Okay, let's look at this Newton's Laws question from November 2018. It's a grade 12 Newton's Law question. So remember, always when we do Newton's Laws, the first rule is you always have to draw a diagram, and that there are two objects, then you are going to draw two diagrams. So a block with a mass of 8 kilograms is placed on a rough horizontal surface. The 8 kilogram block, it's this one over here, which is connected to a 2 kilogram block by means of a light inextensible string passing over a light frictionless pulley, starts sliding from point A as shown below. So fairly obviously this must be the direction of motion. Okay, so I'm going to straight out declare already that the direction of motion is positive. Okay, state Newton's second law in words. You know this law. This is F net equals ma, that if a force is applied to an object, the object will accelerate with an acceleration that is directly proportional to the force and inversely proportional to the mass of the object. Now it says to you, draw a labeled free body diagram for the 8 kilogram block. So that's this block over here. So it is on a surface. So first thing that we do is we draw the dot for the block, and we draw the arrow downwards. Goodness me, that's not a very straight line. We'll do it as straight as possible. So there's the weight. Remember, you have to have the arrow. The arrow has to have a label if you want to mark. Also, bear in mind, this is 4 marks, so we need 4 arrows. So the first force is the weight acting downwards. The second force is the normal force acting at 90 degrees to the surface, and of course the surface is horizontal, as you can see here, then it's acting straight upwards. Then we have here, it said, remember, a rough horizontal surface, so I have friction going in this direction. Let me rub out this 2.2 here. Okay, I have friction going in this direction parallel to the surface, and then now look here, this tension here is going up over the pulley. The tension is at an angle, so I have to make sure that that is not lying in line with the friction, because it's actually at an angle, and we don't need to put the angle in, but it's fine. So it's 4 marks. I've got 4 arrows. I have a dot in the middle. The arrows are coming out of the block. They each have a label, so we need the arrow, the label, and in the correct direction to get all 4 easy peasy marks. Then it says to you, give a reason why, oh wait, when the 8 kilogram block reaches point B, the angle between the string and the horizontal is 15 degrees, okay, that's marked on the diagram, and the acceleration of the system is 1,32 meters per second. Give a reason why the system is not in equilibrium. Well, what things give you equilibrium? If you have equilibrium, you must be moving at a constant velocity, or you must be at rest, stationary, whatever. So this system has an acceleration of 1,32. So my answer here would be because it is accelerating. Okay. Then it says to you, use the 2 kilo mass to calculate the tension in the string. So we know anytime we do a diagram, okay, so this was the 8 kg block. Now we must make a diagram for the 2 kg block. So this one's really easy. Here's the 2 kg block. It's got the string pulling it up, and obviously what is pulling it down? Its weight is pulling it down. So we draw the diagram for the 2 kilo block, and we have the tension in the string pulling it upwards. Okay, so that's an easy force diagram. It's not going to give you any marks, but it helps our brain think. So it says use the 2 kg mass to calculate the tension in the string. So the first thing that we do is we write the formula F net equals ma. Okay, 1 mark for the formula. And now we look, we can only add forces that are in a straight line. So if the direction is positive, direction of motion is positive, remember I declared that right at the start of the question. This thing is moving downwards. Okay, so Fg minus the tension are going to be equal to the mass times the acceleration. So now that we've figured out where the forces are and what they're doing, we can substitute here. We're using the 2 kilo block. So The force due to its mass is 2 times 9.8 minus t. It's going to be equal to 2 times the acceleration, which was 1,32. So now you end up by algebra is something like 19.6 minus 2.64, something like that. So the tension in the string is going to be 16,96 newtons. Okay, so that's the tension in the string. Now it says to you, calculate the kinetic frictional force between the 8 kilo block and the horizontal surface. Okay, so here is the 8 kilo block, here is the horizontal surface. So we're going to use this force diagram for the 8 kilo block. Now, the problem is, remember when we draw a force diagram, we can only add forces that are in a straight line. So if we look at this block, our friction is going backwards along the table and our tension is going up at an angle. Can we add these two forces? Oh, by the way, we're ignoring the force up and the force down because they're not in a straight line. They're at 90 degrees. They're not going to contribute to the friction, the weight, and the normal. So we're only going to focus on the friction and the tension. Okay. Can we add these two forces? No, we may not. Why may we not? Because they are not in a straight line. But what we can do is we can say this tension has got two components, an x component and a y component, and there's a 15-degree angle over here. Okay, so if we want to calculate the kinetic frictional force between the 8 kilo block and the horizontal surface, we can easily use, what number is this? 2.3.3. We will just use Newton's laws again, and we will say F net equals ma. And what forces are there in a line with friction? We said direction of motion is positive, so T minus friction is going to be equal to ma. Okay, and this is the 8 kilo block. Now the tension in the string, remember the tension in the string is the same everywhere throughout the string, the direction just changes. So this tension's going up and this tension's going that way. But now I've not actually stated this correctly here, T minus F, because these are not in a straight line. It's actually the X component of T as I drew over here. So we know a value for T, it's 16,96 newtons. So how do we find the X component? We multiply it by the cos of the angle, because by trigonometry, T cos 15 gives you Tx. Minus F is going to be equal to ma. This mass was a and my acceleration was 1,32. So if you do some geometry here, you end up with F equals 5,82 newtons. Okay, but you're going to find that this is going which way? The friction is going to the left. So it is going to be to the left, because remember, it is a vector. Okay. As the 8 kilogram block moves from B to C, the kinetic frictional force between the 8 kilo block and the horizontal surface is not constant. Give a reason for this statement. Okay. This is because the angle is changing. Theta is changing. If you can't figure out what's happening, think about this. Draw a triangle like this. Effectively, B, C, and this is making a triangle. Can you see that? Let me put it with the highlighter here. Okay. If you look here, from here to here to here is a triangle. If I move from C to the pulley, let me come with another color here. If I come, imagine that's when I start from B. Look at the shape of my triangle. Now if I come from C to there, back to C, can you see that my angle theta over here has changed quite a bit? It's gotten steeper. The string has gotten steeper the closer it gets to the pulley. So the reason why the kinetic frictional force is changing is because theta is changing as the block moves closer to the pulley. Okay, I've put theta as a shorthand for for the angle. So you shouldn't really write theta, you should say the angle is decreasing as the block moves closer to the pulley. Now it says to the horizontal surface on which the 8 kilogram block is moving is replaced by another horizontal surface made from a different material. Will the kinetic frictional force above change? Choose from yes or no. Well, this is fairly obvious. The answer is yes. Think about it. If you are sliding on a smooth concrete floor and you suddenly go onto a rough concrete floor, can you feel a change in the force? Yes, you can. So it is because the coefficient of friction changes due to the nature of the surface. The coefficient of friction changes due to the nature of the surface. Okay, this was quite a simple question. I hope there's nothing confusing you here.